Okay, so let me recap here. So we obtained a 10 comma half approximation, which means that, hey, the chance that we are going to approximate by the distinctive number of distinctive values, elements, within factor 10 is at least half. Okay? That's what it showed. And then, as I said before, so using the median trick, we can reduce the failure probability as small as possible, right? So you can make it arbitrary small delta. Okay. In chapter 3, so I'm going to briefly talk about the new algorithm. So how can we improve this accuracy parameter? Okay. So we want basically we want to estimate within factor say 1 plus epsilon, like 1.1, like arbitrary small, like small factor. So I mean the idea is pretty similar. So but the math is so a little more messy. This algorithm is by Yosef and Jairam and Kumar and Sivakumar and Trevisan. So choose. It's again is two universal hash function. The algorithm is slightly more complicated, but I'm going to simplify it, okay? Because intuition is more important. So as before, we are going to set z to 0, and b is an empty set. And then for when you see j, what you do is that, hey, if number of zeros, right, is bigger than the current z value, it's not z, it's h of j. So if you look at the lecture note, you use another hash function g, but I'm ignoring that because it's just it's some kind of overkill. I mean, by using another hash function, you can even save more space. But let's not worry about that, okay? So what's the idea here? So if you think about the algorithm we learned here, right? Like this algorithm, right? The AMS algorithm. Like what do you do, right? So like say these like what? These say, I mean, you say you represent this as a binary number, right? Then basically you are kind of ignoring all the last digits, right? Because basically you only keep track of the exponent, right? Like how many zeros are there, right? Then obviously you cannot get like arbitrary like accurate, right? Accurate estimation because if you drop like 1, like you round up, round down, you like lose factor 2 at least, right? So this is not a great idea if you really want a very nice accuracy. So what do you want to do, right? So you want to do is that, hey, I want to keep like say like some numbers here, right? I don't mind counting this, but I don't. I think I'm happy to set this to 0, but I keep these in numbers. Okay, and I get a more accurate estimation. That's the idea. So what do we do here? It's very similar, but now what we want to do is that we want to keep some bag here. Okay, this bag is that, hey, you know, z is like z is like how many, okay, so if I would so suppose these are my estimates, right? So at this point, this is like a z. Like at this point, the z is like 5 here, right? So I'm I don't care about the last 5 digits, okay, because they are just too tiny compared to what I care, okay. So then, what's happening, right? But if I z fixed, right, as as I see more elements, distinct elements, I mean this will grow, right? Then in the case, I have to keep too many elements, right? So I want to kind of reduce this, right? So in other words, I need to increase z, right? Then I make this 0 and 0 and so forth, right? And that's what's really happening. So is it back? What do you care here? So okay, suppose this j, a new element, when you see a new element j, okay, it's special, which means that, hey, if I hash this element j, then it's divisible by 2 to the z. Okay, I mean, the chance that, I mean, when you hash when you hash j, the chance that, the probability that its hash value is divisible by 2 to the z will be exactly 1 over 2 to the z, right? Okay, so again, what it means is that, roughly speaking, when you see 2 to the z different elements, then you'll get one more count. Okay, in the case, okay, let's keep the element, the id, and then let's also keep how many zeros it had. Okay, so what it means is that, hey, if it's like say like 8, right? It means that roughly speaking, I kind of believe that there were like 2 to the 8 different elements, something like that. Okay. So anyway, so I'm going to increase back size by adding more. I mean, these are again special elements. But once it becomes too big, right? I don't like that, because I need to make this be small, right? Because otherwise, what's the point of doing trimming algorithms? So I just increase z, so I get increase z, right? Hey, just too much details, right? So let's just ignore this, right? And then, so how do we do that? So basically, I'm going to ignore this this sketch, right? Whose hash values I'm going to ignore element, right? Whose hash values don't end with too many zeros. Okay, then that's how I shrink b. So I keep shrinking b the back, right, until I have a decent size. And then at the end of the day, I only have some special elements, right, whose hash values end with many zeros. Okay, and then the size of b times 2 to the z. I mean, but you see the basic idea, right? So I'm not going to get into details here, but by doing this, you can get epsilon comma delta approximation.